For 0.2 seconds, the universe shook, not metaphorically, not as poetry. Space itself, the fabric of everything, the medium through which light travels, the canvas on which galaxies are drawn, physically compressed and stretched, at a frequency that would register barely as a tone near the edge of human hearing. It happened 1.14 billion years ago. It arrived on Earth on the 14th of January 2025, and the distortion it produced in our detectors was smaller than 1/10,000th the diameter of a proton. We caught it anyway. 2 black holes, each one the collapsed remnant of a star more massive than our own sun could ever dream of becoming, had been orbiting each other for perhaps millions of years, spiraling inward by fractions of a millimeter per orbit, shedding their shared energy as invisible ripples in space-time. Then, in the last fraction of a second of their existence as separate objects, they accelerated to a significant fraction of the speed of light and collided. The energy released in that final merger was equivalent to 3 full solar masses converted instantly and completely into pure gravitational radiation. Not light, not heat, not plasma. Ripples, invisible, weightless, unstoppable ripples that passed through every planet, every star, every galaxy between that event and the 2 L-shaped instruments sitting in the flat countryside of Louisiana and the high desert of Washington state, where, 1 billion years later, they made the steel and glass tremble. 3 questions should be living in your head right now, and I am not going to answer any of them yet. How did we build an instrument sensitive enough to detect a vibration that's small? Why were these particular black holes' masses sitting in a range that our best theories say should be essentially impossible? And what does the strange off-key sound the newly formed black hole made as it settled into existence tell us about the very structure of space and time? To understand what was detected on the 14th of January 2025, and why it matters so profoundly, you need to understand what a gravitational wave actually is, not the poetic description, the real one, because the real one is stranger than the poetry. In 1915, Albert Einstein published his general theory of relativity, and in doing so replaced the Newtonian idea of gravity as a force acting between objects with something far more disorienting. In Einstein's framework, gravity is not a force at all, it is the curvature of space-time, a 4-dimensional fabric woven from 3 dimensions of space and 1 of time, caused by the presence of mass and energy. The Earth does not pull the Moon toward it, the Earth bends space-time around itself, and the Moon follows the curved geometry that results. This is not a metaphor, it is a geometric statement about the actual structure of reality, and here is where it gets genuinely strange. If mass causes space-time to curve, then when mass moves, the curvature moves too. And if a sufficiently massive object accelerates, particularly if 2 massive objects orbit each other, getting closer and closer, then the changing curvature propagates outward through space as a wave. A gravitational wave. It travels at the speed of light. It passes through everything without any interaction. And as it passes, it alternately stretches space in one direction while simultaneously compressing it in the perpendicular direction. Then it does the reverse, then repeats. This means that when a gravitational wave passes through you right now, and several do every hour, the atoms in your body are being stretched and squeezed at an utterly imperceptible scale. The entire Earth deforms slightly as each wave passes through it. The sun wobbles, stars billions of light years away shiver. None of this is detectable by the human body or by any ordinary instrument, because the effect is inconceivably small. But it is real, and Einstein, when he worked out the mathematics in 1916, predicted it with precision. He also, privately, doubted it could ever be measured. He was not wrong to doubt. To detect a gravitational wave from a typical astrophysical event, 2 stellar mass black holes merging at cosmological distances, you need to measure a change in the length of a 4-kilometer instrument that is smaller than 1/10,000th the diameter of a proton. A proton is already roughly 1/1,000,000th the diameter of an atom. You are being asked to measure, with a machine made of steel and glass and mirrors and lasers, a distortion of space so minute that it sits at the absolute boundary of what physics tells us is possible to perceive. The distance between the Earth and the nearest star, Proxima Centauri at 4.2 light-years, would stretch by only about the width of a human hair during a typical gravitational wave event. For most of the 20th century, this measurement was considered unreachable. Even into the 1990s, a significant number of physicists, serious, brilliant physicists, considered the entire LIGO project a well-intentioned waste of money. Nobel laureate Phil Anderson called it, in 1995, a monumentally bad investment. He would later revise that assessment. Somewhat the reason gravitational waves were so long considered undetectable is also, to my mind, the reason they are so extraordinary. The universe emits them from its most violent events: colliding black holes, merging neutron stars, exploding supernovae. But because gravity is the weakest of the four fundamental forces by an enormous margin, the waves it produces carry almost no interaction with matter. A gravitational wave from the collision of two black holes passes through the entire planet Earth without losing even a measurable fraction of its energy. It passes through you, and through a lead wall, and through the core of the Sun, equally unchanged. There is almost nothing you can do to detect something that almost nothing in the universe can stop. Almost. The LIGO detectors, the Laser Interferometer Gravitational Wave Observatory, with facilities at Hanford, Washington and Livingston, Louisiana, use a method of extraordinary elegance: laser interferometry. A laser beam is split into two beams that travel down two perpendicular 4-kilometer arms, each lined with mirrors suspended on wire fibers to isolate them from vibration. The beams bounce back and forth 400 times, giving an effective path length of 100 kilometers in each arm. When both beams return to the central beam splitter, they recombine. Under normal conditions, they are tuned to cancel each other out. The detector sees no light, but if a gravitational wave passes through, it stretches one arm and compresses the other simultaneously, by a distance of about 4 times 10⁻18 meters. The beams no longer cancel perfectly. A tiny pulse of light reaches the photodetector. The universe has spoken. The engineers and physicists who built this system had to contend with noise sources that would give most engineers nightmares. Seismic vibrations from traffic kilometers away. Ocean waves crashing on distant coastlines creating microseismic noise across the entire planet. Quantum noise in the laser itself. The Heisenberg uncertainty principle operating directly on photons. Thermal vibrations in the mirror coatings. Even the gravitational pull of passing clouds. The 40-kilogram mirrors are suspended from quadruple pendulums to isolate them from the ground below. The vacuum inside the beam tubes is better than the vacuum on the surface of the Moon. The laser power in the cavities reaches 200 kilowatts. This is not a modest instrument. This is the most precisely engineered object our civilization has ever built, and it is not alone. By the time of the January 2025 detection, the network had grown to include LIGO's 2 American detectors, the Virgo detector in Cassina, Italy, and Cagra, built inside a mountain in Japan. 4 ears pressed to the fabric of space-time, separated by thousands of kilometers, so that when a wave arrives, the tiny time difference in its arrival at each detector reveals the direction it came from. On January 14, 2025, both LIGO detectors were operating. Virgo and Cagra were not. In one sense, that is a limitation. In another, the fact that the signal was so clear that it barely mattered is the headline. We will come back to that signal. But first, we need to understand what produced it, and why the objects involved should not, strictly speaking, exist. Every black hole detected by LIGO tells a story. It carries encoded in the shape and frequency and duration of the gravitational wave it emits a record of the masses of the two objects that collided, their spins, their orbital configuration, and the mass of the object they became. It is a fingerprint of events that happened hundreds of millions to billions of years ago, compressed into a fraction of a second of signal carried across the universe on the curvature of space itself. The signal detected on January 14, 2025, and formally designated GW25114, carried a mass fingerprint that stopped astrophysicists mid-sentence. The two black holes that produced it had masses of approximately 33.6 and 32.2 solar masses. Together they produced a remnant black hole of roughly 62.7 solar masses, releasing 1 solar masses worth of energy as gravitational radiation in approximately 230 milliseconds. This is a violence that defies comfortable description. In less than a quarter of a second, a mass equivalent to 3 times the entirety of our Sun was converted into pure gravitational energy and radiated away into space, producing a peak power output of roughly 6 times 1049 watts, more than the combined light output of every star in the observable universe for that brief instant. Those mass numbers, 33 and 32 solar masses, place the two progenitor black holes in a region of the mass spectrum that our current models of stellar evolution call the pair instability gap. To understand why this matters, we need to take a brief detour through the life and death of massive stars. When a star several times more massive than our Sun exhausts its nuclear fuel, it undergoes core collapse. The core, no longer supported by the outward pressure of nuclear fusion, collapses under its own gravity. If the core is massive enough, it passes through the neutron star phase and continues collapsing to a singularity, a black hole. The black holes formed this way are called stellar mass black holes, and for decades we assumed most of them would weigh between roughly 5 and 45 solar masses, depending on the mass of the progenitor star and how much material was lost to stellar winds. But stellar physics introduces a complication at higher masses. When a star is very massive, above roughly 100 solar masses, the nuclear fusion processes in its core produce gamma rays energetic enough to spontaneously create electron-positron pairs. This pair production does something unexpected. It robs the core of the radiation pressure that was holding it up. The core destabilizes. In many cases, this triggers an explosion so powerful it completely destroys the star, leaving no remnant at all. This is a pair instability supernova, and its consequence for black hole demographics is stark. Stars that might otherwise have formed black holes in the range of roughly 60 to 130 solar masses instead blow themselves apart completely. The black holes in that range, the ones that would have needed those progenitor stars, simply do not form through normal stellar collapse. This gap is called the pair instability mass gap, and it is one of the most robust predictions of stellar evolution theory. Now look again at GW25011c. Both of the black holes that merged weighed approximately 33 solar masses, comfortably below the gap technically. But just a few months earlier, in November 2023, the LIGO Virgo-Cagra network detected an event designated GW231123, whose properties sit in a far more confrontational position relative to this same theory. The two black holes in that event weighed approximately 137 and 103 solar masses, directly inside the pair instability gap. The resulting merged black hole weighed 225 solar masses, and it is spinning at a rate 4 million times the rotation rate of the Earth. As Cardiff University's Mark Hannam, head of the Gravity Exploration Institute and a member of the LVK collaboration, stated plainly, black holes this massive are forbidden through standard stellar evolution models. Forbidden, not unusual, not rare, forbidden. So there are now at least two competing explanations for how you produce a black hole inside the pair instability gap. And neither of them is comfortable. The first possibility is hierarchical mergers. The black holes we are detecting are not the direct remnants of collapsing stars, but second-generation black holes, products of earlier mergers. A previous pair of smaller black holes collided, producing a black hole of intermediate mass, and that black hole subsequently found a new partner and merged again. This would explain the large masses, but it introduces a geography problem. For a black hole to be captured by another black hole into a tight binary orbit after a merger, the environment needs to be extremely dense, a globular cluster, or the dense inner disk of an active galactic nucleus. In the relatively sparse field environment where most stellar binary systems evolve, Newly formed black holes after a merger would simply escape the system at recoil speeds far too high to be recaptured. Second possibility, which is frankly more disturbing, is that our models of pair instability supernovae are simply wrong, that the forbidden zone is less forbidden than we thought, that stellar evolution at high masses produces outcomes our current physics does not fully predict. And there is a third possibility that nobody wants to invoke, but everybody is whispering about: primordial black holes. Black holes not formed from stars at all, but from density fluctuations in the very early universe, formed in the first seconds after the Big Bang, when regions of space collapsed under their own gravity before stars or galaxies existed. If even a fraction of the black holes being detected by LIGO are primordial in origin, ancient remnants of the universe's first moments, then the history we think we understand about structure formation in the cosmos would need fundamental revision. I want to sit with that for a moment because I think it deserves to land properly. The possibility, not a certainty, not even a probability yet, but a genuine scientific possibility, is that some of the signals being picked up by LIGO are echoes of events that happened in the first minute of the universe's existence, when nothing we would recognize as matter had yet formed. These are not the deaths of stars. They are the footprints of the Big Bang itself, wandering forward through time, carrying their gravitational signatures through 13 billion years of cosmic history before arriving in a pair of L-shaped buildings in rural America to be counted. Whether that interpretation is correct depends on the answer to a question that has not been answered yet. What population statistics do we observe across hundreds of black hole mergers, and do they match the predictions of stellar evolution or something else? The catalogue being assembled by LIGO Virgo Cagra is, in a very real sense, a census of the universe's most violent objects. And that census is beginning to reveal patterns that do not fit any single theory cleanly. Three things are clearly happening at once in gravitational wave astronomy right now. We are confirming the predictions of general relativity with unprecedented precision. We are discovering that the black hole mass spectrum contains objects our stellar evolution models cannot explain, and we are beginning to hear, in the ring-down tones of freshly formed black holes, a symphony that sounds almost but not quite like what Einstein's equations predict. Any one of those three threads would be worth an entire documentary. All three are live and open simultaneously, and they all intersect in the event that this story ultimately turns toward, a signal that arrived on January 14, 2025, carrying within it the clearest confirmation of both Einstein and Hawking's theories ever recorded, and, at the same time, the most provocative unresolved questions the field has yet encountered. Let us build the picture from the very beginning. Two massive stars, orbiting each other in a binary system somewhere in a galaxy not unlike our own, 1.14 billion years ago. They might have been orbiting at a distance of millions of kilometers, taking days or weeks to complete each orbit. Over hundreds of millions of years, they fused hydrogen, then helium, progressing through carbon, oxygen, neon, and silicon in their cores, each successive element squeezed into the next by the relentless gravity of the star's own weight. Eventually, each star ran out of fuel it could fuse. Each core collapsed. In each case, because the cores were massive enough, the collapse did not stop at neutron star density, it continued. The cores became black holes. But here is a subtlety that is often overlooked. When a star collapses and forms a black hole, the collapse is not perfectly symmetric. Material falls inward from slightly different angles. The newly formed black hole receives a gravitational kick, a recoil, that can send it moving at speeds of hundreds of kilometers per second. If the little kick is too large, the black hole simply escapes the binary system entirely, and no merger ever happens. For the two black holes that eventually produced GW 250114, the kicks were apparently gentle enough, or aligned in a way, that the two black holes remained gravitationally bound after both had formed. Two collapsed stellar remnants, orbiting each other, separated by a distance that might have been thousands of times the distance from the Earth to the Moon. completing each orbit in a period of perhaps hours or days. And here is the remarkable thing. At this stage, the system appears stable. Two black holes in a wide orbit could in principle persist for billions of years, but they cannot persist forever. Because they are orbiting each other, they are accelerating, and accelerating masses in general relativity radiate energy as gravitational waves. Not much at first. The power radiated by two compact objects in a wide orbit is negligible, smaller than the power output of an ordinary light bulb. But the consequence of that power loss is inexorable. As energy is radiated away, the orbit shrinks. As the orbit shrinks, the objects orbit faster. As they orbit faster, they radiate more power. The shrinking accelerates, the radiation increases. The orbit shrinks faster still. This is a feedback loop with only one possible ending for most of the lifetime of the system, hundreds of millions of years. The inspiral is glacially slow. The orbit shrinks by micrometers per revolution, but as the separation decreases, the timescale shortens exponentially. In the final year before merger, the orbit has shrunk to thousands of kilometers. In the final week, hundreds. In the final hour, tens. In the final second, the two black holes are separated by a few hundred kilometers, orbiting each other dozens of times per second, moving at tens of % of the speed of light, radiating an extraordinary cascade of gravitational waves whose frequency and amplitude are climbing together in a characteristic sweep called a chirp. That chirp, the rapid rise in frequency and amplitude over the final fraction of a second of the inspiral, is the signature that LIGO is searching for. The frequency rises because the orbital period is shortening. As the black holes spiral inward, they complete their orbits faster and faster, sweeping the gravitational wave frequency upward from a few hertz into the detection band of the instrument, passing through the range of human hearing, 20 to 20,000 hertz, and arriving at merger. If you convert the gravitational wave signal of GW15914, the first detection in 2015, into sound by mapping frequency to audio, it lasts less than 0.2 of a second and sounds something like the low thump of a finger tapping a microphone. A chirp, a blip, a single syllable of cosmic speech. The entire violent end of a billion-year inspiral compressed into a sound that a human throat could almost reproduce. The event, called GW251WA4, detected in January 2025, produced a chirp that lasted approximately 230 milliseconds from the point where the signal entered LIGO's sensitive frequency band. The signal-to-noise ratio, a measure of how clearly the signal stood above the instrument's background noise, was approximately 80. For context, the first detection, GW15014, had a signal-to-noise ratio of about 26. The previous record holder had achieved a signal-to-noise ratio of 42. At 80, GW25011Phi was not merely a strong signal. It was, by some margin, the clearest gravitational wave signal in the history of the science. Parts of the signal reached a local signal-to-noise ratio above 10 standard deviations, a level of significance that, in particle physics, is essentially synonymous with certainty. The reason that clarity matters so profoundly is this: the richer the signal, the more physics you can extract from it. A faint signal tells you roughly how massive the objects were. A clear signal lets you measure spin. An exceptionally clear signal lets you probe what happens in the hundredths of a second immediately after merger. The ring-down phase, where the newly formed black hole, momentarily deformed by the violence of its creation, vibrates like a struck bell and settles into its final stable state. And the tones of that ringing contain information that physicists have been waiting decades to read. The ring-down is governed by a set of predictions embedded in general relativity called the Kerr solution, named for the New Zealand mathematician Roy Kerr, who in 1963 derived the exact mathematical description of a spinning black hole. The Kerr solution predicts not just one frequency of ring-down, but a series of overtones, each with its own frequency and decay rate, determined by and only by the black hole's mass and spin. This is not a detail, it is a deep statement. The Kerr solution says that once the ring-down has begun, the entire subsequent behaviour of the newly formed black hole, Every frequency, every decay timescale is uniquely determined by two numbers, mass and spin, nothing else. No memory of how it formed, no trace of its prior structure, no imprint of the collision geometry. Everything except mass and spin is radiated away in the ring-down and lost. This is the content of what is called the no-hair theorem. The no-hair theorem is one of the most philosophically striking predictions in all of physics. It says that black holes are the simplest macroscopic objects in the universe. A black hole of 60 solar masses, spinning at a dimensionless spin parameter of 0.68, is completely and utterly identical to any other black hole of 60 solar masses spinning at 0.68, regardless of whether it formed from a stellar collapse, a binary merger, the collapse of a globular cluster, or any other violent process the universe might produce. Every black hole of the same mass and spin is the exact same object. They have no individual identity. They carry no scars, no histories. They are, in a sense, the most democratic objects in nature, reduced to their absolute minimum distinguishing characteristics, stripped of every particularity. To test this prediction properly requires measuring multiple overtones in the ring-down, the fundamental frequency, and at least one overtone, and checking whether the ratio between them matches the Kerr prediction precisely. This has never been possible before GW250114, because no previous signal was loud enough to resolve the first overtone with confidence. GW250114 was loud enough, and the implications of what the analysis found, and what it narrowly failed to prove, are the beating heart of why this particular detection deserves the attention of anyone who has ever wondered whether the universe is as orderly as our equations suggest. But there is one more complication to address first. One more layer of mystery to stack, because that is precisely how this story is structured by the universe itself. The two black holes that produced GW25011 had, according to the waveform analysis, very low individual spins, at most about 0.25 out of a maximum possible value of 1.0. This is already interesting. We do not fully understand the distribution of black hole spins in the population, and very low spins might indicate particular formation channels. But the merged black hole had a spin of 0.68, the orbital angular momentum of the two black hole system. The momentum of rotation of the pair around their shared centre of mass was converted into the spin of the remnant. This is expected. What is less expected is that the merged spin of 0.68 places the final black hole comfortably in the regime where general relativity makes specific, testable predictions about the ring-down that differ from the predictions for more slowly spinning objects. The ring-down of a Kerr black hole, a spinning black hole, is described by a mathematical framework called black holes spectroscopy, by analogy to the way atomic spectroscopy allows chemists to identify elements by the frequencies of light they emit. In black hole spectroscopy, the frequencies and damping times of the ring-down modes play the role of spectral lines. If the remnant is truly a Kerr black hole, if general relativity is correct, then all the modes must be consistent with a single pair of values, mass and spin. Any deviation would signal either new physics beyond general relativity or the presence of some exotic compact object that is not precisely a black hole. This is where GW25014 delivered something unprecedented. For the first time in any gravitational wave signal, the first ring-down overtone, the Kerr overtone, was identified with a significance of 4.1 standard deviations, not merely hinted at, detected. The overtone's frequency and decay time were consistent with what a Kerr black hole of the measured mass and spin should produce. Hawking's area theorem, the prediction that the total surface area of a merged black hole must equal or exceed the combined surface areas of the two progenitor black holes, was also confirmed directly with this signal for the first time. The two progenitor black holes had a combined event horizon area of approximately 240,000 square kilometres, roughly the area of the United Kingdom. The merged black hole's event horizon measured approximately 400,000 square kilometres, roughly the area of Sweden. The area increased. Hawking was right. 3 open questions remain though. and they are not small ones. On September 10, 2025, almost exactly 10 years to the day after GW1 FIVZO94 was detected, though it was not announced until February 2016, the LIGO-Virgo-CAGRA collaboration published the full analysis of GW250114 in Physical Review Letters. The paper was titled, "With the understated precision that physicists favour when they believe they have done something important, GW25011, Testing Hawking's Area Law and the Kerr Nature of Black Holes." The results confirmed what earlier preliminary analysis had suggested, with tightened error bars and the kind of statistical authority that makes physicists comfortable using the word General relativity passed the test. The Kerr solution for rotating black holes. Roy Kerr's 1963 masterwork, derived purely from the mathematics of curved space-time, accurately predicted the ring-down of a black hole formed from the merger of two objects that did not exist when Kerr wrote his equations, in a collision that happened before the first animals appeared on Earth, detected by an instrument that would have seemed like pure fantasy to most physicists in 1963. I find it difficult to convey just how strange that chain of events is. A mathematician in New Zealand, working with pen and paper in 1963, solved equations that Einstein had written in 1915 and produced a description of rotating black holes that was confirmed 60 years later by detectors that had to measure distortions of space 1/10,000th the diameter of a proton. The confirmation arrived courtesy of a gravitational wave that had been travelling for over 1 billion years before anyone on Earth existed to receive it. The universe is not obligated to follow equations written by humans, and yet the Hawking area theorem confirmation is, if anything, even more philosophically loaded. Stephen Hawking derived the area theorem in 1971, the same year that man last walked on the moon, 4 years before the first personal computer was sold commercially, a full 22 years before the World Wide Web reached the public. Hawking proved mathematically that the event horizon area of a black hole can never decrease. The event horizon is the boundary of no return, the surface from inside which nothing, not even light, can escape. Its area is proportional to the black hole's mass squared, adjusted for spin. Hawking showed from first principles of general relativity that any physical process, including mergers, which involve both mass accretion and spin, must leave the total horizon area equal to or larger than what it started with. This is not a trivial result. It means black holes obey something that looks, structurally, like the second law of thermodynamics, the law that entropy never decreases in a closed system. Jacob Bekenstein, a physicist who worked with Hawking and died far too young in 2015, made this analogy explicit. If the event horizon area behaves like entropy, then black holes must have a temperature, and if they have a temperature, they must radiate. This led Hawking to his most celebrated prediction, that black holes slowly evaporate, emitting what we now call Hawking radiation, by a quantum mechanical process at the horizon. Hawking radiation has never been directly observed. It is too faint from any astrophysical black hole to detect, but it sits at the very centre of the ongoing effort to reconcile general relativity with quantum mechanics. The area theorem, confirmed by GW250114, is a thread that leads directly into the deepest unsolved problem in physics. The two black holes that merged to produce GW250114 had been, for most of their inspiral lifetime, almost perfectly matched in mass, 33.6 and 32.2 solar masses, a mass ratio very close to 1:1. This near symmetry is itself informative. It suggests they likely formed together from a binary star system, rather than being dynamically captured from separate systems after formation, since dynamically captured binaries tend to have more asymmetric mass ratios. Their individual spins were low, which may suggest they formed through a channel where the pre-collapsed stars had shed most of their angular momentum through stellar winds. The merger produced a black hole spinning at 0, 68 times the maximum possible rate, a rate of roughly 100 revolutions per second for an object of 62.7 solar masses, 100 revolutions per second, an object 3 times the mass of the Sun, whose event horizon is roughly the size of a small country, spinning 100 times every second. There is no scale of human experience that makes that comprehensible. The fastest spinning pulsars, neutron stars, rotate at up to 716 times per second, but they are neutron stars, perhaps 20 kilometers across, with a mass not much more than the Sun, a black hole of 62. 7 solar masses has a Schwarzschild radius of approximately 93 kilometers, an event horizon the size of a mid-sized city, rotating 100 times per second. The surface of the event horizon, if we could place a notional marker on it, would be moving at a substantial fraction of the speed of light. But the signal from GW 250114, extraordinary as it was, is not the most puzzling signal in the current catalogue. That distinction belongs to GW 231123, the event detected in November 2023, whose initial findings were published as a preprint in July 2025 and represent, by some margin, the most theoretically disruptive detection in the history of gravitational wave astronomy. GW 231123 was produced by the merger of 2 black holes with masses of approximately 137 and 103 solar masses. The resulting black hole has a mass of 225 solar masses. Those progenitor masses sit squarely inside the pair instability gap, the range that stellar evolution theory says black holes cannot occupy if they formed through ordinary stellar collapse. And the ring-down signal from GW 231123 is producing tones that do not straightforwardly match what the Kerr solution predicts. To be precise about what do not match straightforwardly means in this context, the ring-down of GW 231123 appears to contain at least 2 distinct overtone frequencies, which is itself consistent with what general relativity predicts for a rapidly spinning Kerr black hole. But the combination of those tones does not correspond neatly to the pattern expected for a black hole of the inferred mass and spin. The researchers at the Flatiron Institute's Center for Computational Astrophysics, who played a leading role in the analysis, described the situation cautiously. As Max Izzy of the CCA put it, in this system we see at least 2 separate tones emitted by the remnant as it is in this phase, but not in a pattern that corresponds straightforwardly to what we might expect for such systems. There are 3 candidate explanations. The first is that the 2 progenitor black holes were spinning in opposite directions, anti-aligned spins, and underwent a phenomenon called spin precession as they approached merger. Their spin axes wobbled like gyroscopes, creating a highly distorted asymmetric merger geometry that produced a strongly perturbed remnant with an unusual ring-down pattern. This would be consistent with general relativity just at an extreme and poorly sampled part of parameter space. The second explanation is that our numerical relativity simulations, the supercomputer calculations that predict what gravitational wave signals should look like from mergers with various parameters, are simply not accurate enough at these extreme mass ratios and spin configurations to match what the detectors are seeing. The third explanation is that we are seeing early signatures of physics beyond general relativity, some modification or extension of Einstein's theory that manifests at the extreme conditions produced by merging black holes of this extraordinary mass. The team is not claiming the third option. Not yet. The data are not clean enough, the error bars not small enough, the theoretical understanding not complete enough. But none of them are ruling it out either. Will Farr, whose gravitational wave astronomy group at the Flatiron Institute led much of the analysis, put it with characteristic precision. We still have many questions about these types of signals, so we cannot say with full certainty yet what it all means. But to me, all of these interwoven open questions, ranging from the behaviour of dynamic spacetime to the lives and deaths of stars, are extremely exciting. This is, I think, exactly the right emotional register. Not alarm, not certainty of a paradigm shift, but a clear-eyed recognition that the data are showing something that current models do not fully explain, and that the explanation, when it arrives, will tell us something we did not know about either the deaths of very massive stars, the dynamics of spinning black holes, or the fundamental structure of space-time. Any of those outcomes would be worth the decades it took to build the instruments that made the measurement possible. And the story of those decades is, to my mind, the most human part of this entire enterprise. It is a story about one man, one idea, and 50 years of institutional skepticism, and what it costs to be right before everyone else is ready to believe you. In the early 1970s, a physicist at MIT named Rainer Weiss sat down and wrote a calculation that changed the history of science. He was not sure at the time that it would. He had been thinking about gravitational waves, Einstein's prediction, still unverified, and about whether it might be possible to detect them using laser interferometry. He had taught general relativity to students and felt, with the particular unease of a careful thinker, that he did not fully understand the answer to a question one of his students had asked. Could you really detect a gravitational wave with a free body measurement? He went home and worked it out. Then he wrote it up. The result was a 1972 MIT technical report, not even a proper journal article, a technical report, that laid out in remarkable completeness the concept of a kilometre-scale laser interferometric gravitational wave detector. He estimated the sensitivity that would be required to see astrophysical sources. He calculated the dominant noise sources, seismic noise at low frequencies, thermal noise in the mirror suspensions at intermediate frequencies, shot noise in the laser at high frequencies. He described the basic architecture. He got most of it right on the first attempt, decades before the instrument was built. Weiss had been born in Berlin on September 29, 1932, into a Jewish family during one of history's more dangerous periods to be Jewish in Germany. His father, a neurologist, moved the family to the United States when Rainer was a child. He grew up in New York, developed an early passion for electronics, repairing radios, building hi-fi systems, and eventually wandered into physics at MIT, where he would spend most of his professional life. He was not a conventional academic success story. He failed out of MIT as an undergraduate the first time, distracted by a love affair. He returned, eventually completed his PhD, and became a professor, teaching and thinking and building instruments with a hands-on engineer's instinct that set him apart from more purely theoretical colleagues. The early years of LIGO were not triumphant. Weiss proposed the project, joined forces with Kip Thorne at Caltech and Ronald Drever, a brilliant if difficult Scottish experimentalist who had independently developed similar ideas. The three formed an uneasy alliance. Getting funding for the project meant navigating an academic community that contained many people who believed the whole enterprise was a category error, that building a 4-kilometre detector to look for signals that most theorists considered too faint to measure was not physics. It was wishful thinking with a price tag. The National Science Foundation, which would ultimately fund LIGO at a cost of roughly $1 billion over its construction phase, required significant convincing. Barry Barish, who joined the project in 1994 and reorganised it into a functioning large-scale collaboration, eventually earning a share of the Nobel Prize for doing so, has described the project in its early years as on the edge of cancellation on more than one occasion. The personal cost to Weiss was not trivial. He spent decades defending a project that many of his peers considered speculative at best. He spent years managing the scientific and personal conflicts that arise when three strong-willed experimentalists are asked to collaborate on something that has never been built before. He watched the project grow, the budgets expand, the timescales stretch. Initial designs were replaced, upgraded, replaced again. The first iteration of LIGO, called Initial LIGO, operated from 2002 to 2010 and detected nothing, which was not surprising. It was known from the beginning that Initial LIGO probably lacked the sensitivity to see any astrophysical source with a reasonable event rate. It was a proof of concept, a technology demonstrator, a down payment on advanced LIGO, the upgraded version that would finally have the sensitivity to see the real thing. Advanced LIGO came online in its first engineering run in September 2015. Weiss was 82 years old. He had been working toward this moment for more than 40 years. On September 14, 2015, at 9:50:45 Universal Coordinated Time, during the first engineering run, before the official science run had even begun, the LIGO detector at Livingston, Louisiana, registered a signal. 7 milliseconds later, the Hanford, Washington detector registered the same signal. The time difference of 7 milliseconds is consistent with a signal travelling at the speed of light between the two detectors from a direction in the southern sky, which places the event origin in the southern celestial hemisphere. The signal rose in frequency from 35 Hz to 150 Hz over 0.2 seconds. The amplitude of the distortion, the fractional change in the length of the 4-kilometre arm, was 1.0 times 10 minus 21. The researchers who saw the signal initially thought it was an injected test, a fake signal deliberately inserted into the data stream to test the analysis pipeline's ability to detect it. This is a real and routinely used procedure in gravitational wave astronomy, and it had happened before. Nobody told anyone it was real. Nobody wanted to be the person who declared the discovery of gravitational waves, and then had to retract the statement a week later when somebody found the test injection that caused the false alarm. The validation process took 5 months. Every possible noise source was investigated. The hardware injection records were checked. No test had been injected. The signal was correlated between two detectors separated by 3,002 kilometers on a timescale consistent with light travel time, in a configuration consistent with the sky position of the source. The waveform matched, to extraordinary precision, the numerical relativity prediction for the merger of two black holes of 36 and 29 solar masses. The paper announcing the discovery was published in Physical Review Letters on February 11, 2016. GW150914, the gravitational wave event of September 14, 2015, had been produced by a collision of two black holes 1.3 billion light-years from Earth, releasing energy at a peak power of 3.6 times 1049 watts. 3 solar masses of energy had been converted into gravitational radiation in a fraction of a second. Einstein's prediction of 1916, which Einstein himself had doubted could ever be verified, had been confirmed by direct measurement. A new window on the universe had opened. Weiss learned of the confirmation of GW1591T's authenticity in late 2015, before the announcement. He has said that his reaction was not the triumphant exultation one might expect from a man who had spent 4 decades pursuing this result. It was closer to disbelief, followed by a long, quiet sitting with the reality of what had happened. This is consistent with what I understand from reading about him, of his character. A man who was deeply serious about the quality of his evidence, who had spent his career defending a project that many considered hopeless, who had perhaps learned to hold his certainty lightly, hedged against the possibility of being wrong once more. He was not wrong. He was awarded the 2017 Nobel Prize in Physics alongside Kip Thorne and Barry Barish for decisive contributions to the LIGO detector and the observation of gravitational waves. He was 85 years old at the time of the award, the oldest Nobel laureate in physics in history at that point. At the ceremony in Stockholm, he was celebrated not as someone who had made a single breakthrough discovery, but as someone who had persisted in building an instrument that the scientific community had doubted for decades, at enormous personal and professional cost, because he believed correctly that the universe had something to say and that we could build the ears to hear it. Rainer Weiss died on August 25, 2025. He was 92 years old. He died less than 3 weeks before the publication of the GW250114 analysis, the paper that confirmed, with a signal-to-noise ratio of 80, the area theorem of Stephen Hawking and the Kerr nature of rotating black holes. The instrument he conceived in 1972 had, in the 10 years since its first detection, catalogued nearly 400 gravitational wave events, transformed our understanding of the black hole mass spectrum, confirmed multiple predictions of general relativity that had never previously been testable, and was, at the moment of his death, still operating, still listening, still accumulating data from the most violent events in the universe. I think it is worth pausing here to consider what that kind of dedication actually costs. 40 years of defending a project that many thought was folly, 40 years of grant cycles, peer reviews, budget negotiations, institutional politics, personal conflicts within the collaboration, and the steady awareness that the measurement you are working toward might not happen within your professional lifetime, or possibly your lifetime at all. Weiss was not alone in this. Thousands of scientists and engineers contributed to LIGO over its history, and the Nobel Prize's limitation to 3 recipients is one of the more poorly suited conventions of the awards system when applied to a discovery of this nature. But Weiss was the origin point, the person who wrote down the idea and refused to let it go. There is a sentence from an MIT News interview with Weiss, conducted in 2016 just after the GW15091 fee announcement, that I return to when I think about what scientific persistence actually looks like. I was always convinced that if you made the instrument sensitive enough, you would see something, whether it would be gravitational waves from the sources we expected, or something completely new. The universe always surprises you. That was the reason to build it. The universe always surprises you. That was the reason to build it. By the time of the GW25114 detection in January 2025, LIGO had been through multiple upgrade cycles since the original advanced LIGO configuration of 2015. Each upgrade had improved sensitivity in different frequency bands, reduced different categories of noise, extended the reach of the detectors to larger distances and thus larger volumes of the universe. The 4th observing run, 04, ran from May 2023 to November 2025, and by the time it concluded, the global network of LIGO, Virgo and Cagra had catalogued approximately 390 gravitational wave events. By March 2025, the 200th detection of the current run had been recorded, the 200th detection in a single observing run. In the first observing run in 2015, there was the transformation from a single, miraculous detection to an industrial-scale catalogue of cosmic violence is one of the more underappreciated scientific revolutions of the early 21st century. LIGO has become, in a decade, not just a proof of concept, but a survey instrument, a gravitational wave telescope that is systematically mapping the population of compact objects in the universe, measuring their mass distribution, their spin distribution, their merger rate, their formation channels. The individual events are still extraordinary, but the population is where the deepest physics lives, and the population contains surprises that Weiss himself might have found, if not shocking, then at minimum deeply satisfying in their capacity to keep the questions alive, which is, as he said, exactly the reason to build the thing. The gravitational wave catalogue, assembled by the LIGO Virgo Cagra network over 10 years of operation, represents something genuinely unprecedented in the history of observational astronomy, a census of the universe's most extreme objects, conducted not through electromagnetic radiation but through the curvature of spacetime itself. Understanding what that census is telling us requires stepping back from individual events and looking at the population as a whole. And the population contains structures, anomalies, and implications that are beginning to reshape our models of how stars live and die. Let us start with what we know. As of the end of the 4th observing run in November 2025, the catalogue contains approximately 390 gravitational wave candidates with a false alarm rate low enough to merit scientific analysis. The overwhelming majority are binary black hole mergers. A smaller fraction involve at least one neutron star. A very small number are of uncertain classification, compact objects in mass ranges where both neutron stars and black holes might plausibly be found. Each event contributes a measurement of 2 progenitor masses, 2 progenitor spins, a distance and a supposition. Taken together, these measurements constitute a statistical sample of the binary compact object population across a significant fraction of the observable universe. The mass distribution revealed by this catalogue is one of the most discussed topics in gravitational wave astrophysics. Several features emerge clearly. There is a concentration of black hole masses around 10 solar masses, consistent with what we might expect from the collapse of moderately massive stars. There is a secondary feature around 35 solar masses, where the GW150914 progenitors lived. That is slightly harder to explain from standard stellar evolution. There appears to be a relative paucity of black holes in the range of 50 to 80 solar masses, which might correspond to the lower boundary of the pair instability gap. And then there are the outliers, the GW231123 progenitors at 137 and 103 solar masses, sitting comfortably inside the gap's forbidden territory, demanding an explanation. The detection rate has also been continuously improving. Early observing runs detected events at a rate of roughly 1 per week of operation. By the fourth observing run, the rate had increased to several per week, driven by improved detector sensitivity that expanded the accessible volume of space. This is not merely a technical milestone, it is an epistemological one. A catalogue of a few dozen events is interesting, but statistically limited. A catalogue of hundreds of events begins to tell you about rare populations that would never appear in a small sample. GW231123. An event whose progenitor masses are so unusual that the estimated occurrence rate in any given galaxy is perhaps once per 100 million years, was only detectable because the LIGO network was listening to a volume of space large enough to contain millions of galaxies simultaneously. The spin distribution of the black hole catalogue is a second major source of scientific information. Black hole spin encodes information about how the progenitor system evolved. In a binary star system, where both stars orbit each other in the same direction and evolve without significant interaction, the spins of the resulting black holes tend to be aligned with the orbital angular momentum. Both black holes spin in the same direction as they orbit each other. In a dynamically assembled binary, two black holes that were captured into a binary orbit by gravitational interactions in a dense stellar environment, like a globular cluster or a galactic nuclear star cluster. The spins are randomly oriented, producing misaligned or anti-aligned spin configurations. The LIGO catalogue shows evidence for both populations. Some events show signatures consistent with aligned spins and isolated binary evolution. Others show evidence for spin precession, the wobbling of the orbital plane caused by misaligned spins that points toward dynamically assembled systems. This is, on reflection, exactly what we should expect from a universe with multiple black hole formation channels operating simultaneously. The gravitational wave catalogue is not telling a single clean story about how binary black holes form. It is telling a complicated, richly textured story about at least two and possibly more formation pathways operating in parallel in different galactic environments, producing overlapping but distinguishable mass and spin distributions. The hierarchical merger hypothesis, the idea that some detected black holes are themselves products of earlier mergers, making them second-generation objects, has gained significant traction from catalogue analysis. Several events in the catalogue show mass ratios, total masses, or spin configurations that are difficult to explain through standard single-generation stellar evolution, but become more explicable if one or both objects is a merger remnant. GW190521, detected in 2020, had progenitors of approximately 85 and 66 solar masses, both sitting inside the pair instability gap, and is one of the strongest candidates for a hierarchical merger event. For two such heavy black holes to have found each other, formed a tight binary, and merged within the age of the universe in a random stellar field environment, would require a staggeringly unlikely sequence of events. In the densely packed environment of an active galactic nucleus disk, the swirling, gas-rich region around a supermassive black hole, the conditions for repeated mergers and recapture of merger remnants are much more favourable. There is something extraordinary about that picture if you let it fully form in your mind. Imagine a galaxy with a supermassive black hole at its centre, surrounded by a disk of gas hundreds of light years across, seeded with compact objects, stellar mass black holes and neutron stars that have migrated inward over millions of years. In the disk, the gas provides drag and angular momentum exchange, allowing compact objects to find each other, enter closed binaries, merge and merge again. The black holes grow with each merger. Second generation, third generation, possibly fourth generation products are circling the supermassive black hole, waiting for their next partner. This is black hole evolution as a kind of cosmic ecology, a web of mergers and growth playing out over billions of years, hidden from electromagnetic observation because black holes do not shine, visible only in the gravitational waves their collisions emit. If a significant fraction of the binary black hole mergers in the LIGO catalogue are occurring in active galactic nucleus disks, then the gravitational wave catalogue is not merely a census of compact objects, it is a probe of the internal dynamics of galactic nuclei across cosmic time. The mass function of the merger products, their spin orientations, their merger rates as a function of redshift. All of these carry information about the density, geometry and composition of the disk environments where the mergers are occurring. LIGO is, from this perspective, a telescope pointed not at compact objects per se, but at the internal machinery of galaxies, and the machinery is not quiet. The LIGO Virgo Cagra network is not the only gravitational wave observatory operating right now. In 2023, the Nanograv Pulsar Timing Array collaboration, which monitors the arrival times of radio pulses from a network of millisecond pulsars distributed across our galaxy, announced the detection of a stochastic gravitational wave background, a low-level, isotropic hum of gravitational radiation permeating all of space. This background does not come from individual detectable events, but from the superposition of gravitational waves emitted by millions or billions of merging supermassive black holes throughout cosmic history. The collisions of the behemoths at the centres of galaxies when those galaxies themselves merge. The gravitational wave background is to LIGO what the cosmic microwave background is to optical astronomy, a diffuse, pervasive signal from a much earlier and much more violent epoch of the universe's history. The detection of the gravitational wave background by Nanograv and 3 other independent pulsar timing array collaborations in 2023 opened a third window on gravitational wave astronomy. LIGO sees the stellar mass range, black holes of tens of solar masses. Pulsar timing arrays see the supermassive range, black holes of millions to billions of solar masses. Between them lies an intermediate frequency band where black holes of hundreds to hundreds of thousands of solar masses should be emitting gravitational waves. And that band is currently dark, inaccessible to both LIGO, which is sensitive at frequencies too high, and pulsar timing arrays, which are sensitive at frequencies too low. This is the gap that the Laser Interferometer Space Antenna, LISA, is designed to fill. And LISA, currently planned for launch in 2035, represents the next major chapter in this story. But before we get there, we need to reckon with something that has been building quietly in the background of everything we have discussed. The fact that the LIGO network, for all its extraordinary sensitivity, is operating close to the boundary of what it can detect with current technology, and that the next generation of instruments will open the universe in ways that make the current catalogue look like a sketch. The universe, in other words, has been saving its best material. Let us be precise about where we stand. As of the end of 2025, LIGO Virgo Cagra has detected approximately 390 gravitational wave events. The large majority are consistent within the measurement uncertainties of each individual event with the predictions of general relativity. The population statistics are broadly consistent with at least some binary black holes forming through stellar evolution in isolated binaries, and others forming dynamically in dense environments. The No-Hair theorem and Hawking area theorem have been confirmed, with GW2T50114 providing the most stringent test to date. The speed of gravitational waves has been measured to be equal to the speed of light to a precision of 1 part in 1015 using the coincident detection of gravitational waves and a gamma-ray burst from the neutron star merger GW17081 SEMS in 2017, which arrived within 1.7 seconds of each other after travelling 130 million light-years. All of this sounds like closure. It is not. The confirmation of general relativity's predictions is wonderful, but it is the confirmation of what we expected, and what we expect cannot tell us what we are missing. The most consequential physics is always hiding in the residuals, the deviations from prediction, the anomalies that don't fit, the events that require an explanation none of the current models provide cleanly. The GW231123 anomalous ringdown is one such residual. The pair instability mass gap violations are another, and there are subtler issues running beneath the catalogue as a whole that are accumulating into a pattern that theorists are beginning to take seriously. The first is the spin alignment question. As mentioned, the LIGO catalogue shows evidence for two populations of binary black holes with different spin distributions. This is qualitatively consistent with models, but the quantitative details, the exact fraction of aligned versus misaligned systems, the relationship between mass and spin alignment, the evolution of these quantities with redshift, do not yet match any single formation model cleanly. Some fraction of events show spin precession signatures that suggest significant spin-orbit misalignment, but not as many as the dynamical formation channel would naively predict. The current data are consistent with a mixture of formation channels, do not tightly constrain the relative contributions of each channel at different mass ranges and redshifts. The second is the mass ratio distribution. Most binary black hole mergers in the catalogue involve two objects of roughly similar mass ratios close to 1:1. This makes sense for isolated binary evolution, where the two stars formed together from the same molecular cloud and evolve in lockstep. But the population also contains several events with extreme mass ratios, one black hole much more massive than the other, which are harder to explain from isolated binary evolution and point toward dynamical assembly or accretion-driven growth in a gaseous environment. The distribution of mass ratios across the catalogue contains subtle features that are beginning to discriminate between formation models, but not yet definitively. The third open question is perhaps the deepest, and it is one that the gravitational wave data are not on their own able to answer. It is the question of what happens inside a black hole. The event horizon is the boundary of observational access. Nothing from inside a black hole can ever reach our detectors, whether they be gravitational wave interferometers or electromagnetic telescopes. The ringdown signal in GW25011 probes the geometry of space-time just outside the newly formed event horizon, the region where the perturbed geometry is settling into its Kerr equilibrium, but it does not and cannot probe the interior. The interior of a black hole, as described by general relativity, contains a singularity, a point or region where the density of matter and the curvature of space-time become mathematically infinite. This singularity is not a physical prediction. It is a sign that general relativity is breaking down, that the equations are telling us they have reached the limit of their applicability and something beyond is needed. Something beyond is, in the consensus of physicists, a theory of quantum gravity, a framework that reconciles general relativity with quantum mechanics. Quantum mechanics, which governs the behaviour of matter and energy at subatomic scales, contains no description of gravity. General relativity, which governs the behaviour of space and time on large scales, contains no quantum mechanical structure. The two frameworks are not merely mathematically different, they are conceptually incompatible. General relativity is a deterministic, smooth, continuous theory of curved space-time. Quantum mechanics is a probabilistic, discrete theory of fields and particles. At the singularity of a black hole, where densities reach Planckian values and the volume being described shrinks to subatomic scales, both theories apply simultaneously, and neither can be trusted. The gravitational wave catalogue is not going to resolve this problem directly, but it is providing constraints. Black hole spectroscopy, The measurement of ring-down frequencies and damping times is sensitive to modifications of general relativity that predict different quasi-normal mode spectra for post-merger black holes. Several models of quantum gravity and modified gravity theories predict small but potentially detectable deviations from the Kerr quasi-normal mode spectrum. The current data are consistent with the Kerr prediction, which means those modifications must be small, below the detection threshold of the current instruments. The next generation of detectors, with sensitivities an order of magnitude better than LIGO's, will be able to push those constraints down by orders of magnitude, potentially reaching the level at which quantum gravitational corrections might plausibly manifest. The no-hair theorem is a closely related pressure point. The theorem says that a black hole is completely characterized by mass, spin, and charge. Any deviation from this, any residual structure, any hair that carries information beyond these three numbers, would signal new physics. Black hole spectroscopy with GW250114 confirms the no-hair prediction to the level accessible with current signal quality. But the theorem has theoretical vulnerabilities. In certain models of quantum gravity, the singularity inside a black hole is replaced by a quantum structure, a Planck density core of quantum spacetime, that might produce quasi-normal mode spectra slightly different from the pure Kerr prediction. In models motivated by black hole information theory, the debate over what happens to information that falls into a black hole. The near-horizon geometry might be modified by quantum effects in ways that alter the ring-down. These are speculative possibilities, but they are testable with sufficient detector sensitivity. The question of whether a black hole truly has no hair is, in the strictest sense, still open. There is also a structural question about the gravitational wave background detected by nanograv that deserves attention here. The background discovered in 2023 is broadly consistent with the expected signal from merging supermassive black hole binaries throughout the history of the universe. But the amplitude of the background is at the higher end of what binary merger models predict, and its spectrum contains features that might indicate contributions from additional sources. Cosmic strings, early universe phase transitions, or gravitational waves from the inflationary epoch itself. If any fraction of the gravitational wave background originates from processes in the very early universe, from inflation, from a first-order phase transition associated with electroweak symmetry breaking, from the formation of cosmic strings during symmetry breaking in the early universe, then pulsar timing arrays are not merely measuring the mergers of supermassive black holes. They are listening to the echoes of the processes that shaped the structure of matter and space in the first microseconds of the Big Bang. This is not currently provable. The nanograv data are consistent with supermassive black hole binary mergers as the primary source, and there are enough uncertainties in the supermassive black hole binary population models that invoking additional sources is not yet necessary. But the data do not rule out additional contributions, and the next decade of pulsar timing array observations will sharpen those constraints. Then there is the information paradox itself, arguably the deepest open problem in theoretical physics, brought into sharp relief by the observation of black holes merging in real time. When matter falls into a black hole, the information that describes it, the quantum mechanical state of every particle, every spin, every entanglement, is apparently lost. It crosses the horizon, reaches the singularity, and vanishes. But quantum mechanics has a fundamental law that says information cannot be destroyed, that the universe's total quantum state evolves deterministically and reversibly. If black holes destroy information, then quantum mechanics is wrong at black hole boundaries. If quantum mechanics is correct, then something must retrieve or encode that information, perhaps in the Hawking radiation that slowly evaporates the black hole over cosmological timescales. But Hawking's original calculation suggested the radiation was purely thermal, that it carried no information about what fell in. This contradiction, the black hole information paradox, has been the central unresolved tension in theoretical physics Since the 1970s, recent theoretical work, particularly developments related to the concept of island contributions to black hole entropy, drawing on tools from quantum information theory applied to quantum gravity, suggests that information is indeed preserved during black hole evaporation, and that the entropy of the Hawking radiation does eventually begin to decrease, as required by unitarity, after a very long evaporation period called the page time. But this resolution is not yet a complete theory. It is a partial insight, a structural understanding that something must be happening to preserve information without yet specifying the exact mechanism. The GW 2501114 confirmation of the Hawking area theorem is relevant here. The area theorem is a classical statement about the growth of event horizon area, which by Bekenstein-Hawking thermodynamics corresponds to entropy growth. The quantum correction, Hawking radiation, entropy decrease via evaporation operates on completely different timescales. For a black hole of 62.7 solar masses, the Hawking evaporation timescale is approximately 1,074 years, a number so far beyond the current age of the universe that it might as well be forever. The information stored in that black hole, whatever it is, will not come out in any timescale relevant to human astronomy. This is not a failure of our instruments. It is a fundamental feature of the physical situation. The LIGO network probes the formation and early ringdown of black holes. Quantum gravitational effects on the information content take 1,074 years to manifest. The two timescales are separated by 64 orders of magnitude. No instrument conceived by current or foreseeable future technology can bridge that gap directly. The information paradox will be resolved, if it is resolved, by theory, not by measurement. And yet the measurements matter for the theory because every confirmed prediction of general relativity in the strong field regime, every verified ringdown frequency, every confirmed no-hair measurement, every tested area theorem, constrains the space of possible theories that could replace or extend general relativity in the quantum domain. The data from GW 25011 and the broader LIGO catalogue are not merely confirmations of Einstein. They are precision measurements that any successful theory of quantum gravity must reproduce. They are the empirical floor that theory must stand on. But there are two more unresolved questions that belong in this chapter, not because they are the deepest, but because they are the most immediately pressing for the next decade of gravitational wave astronomy. The first is the Hubble tension. The universe is expanding, and the rate of that expansion, called the Hubble constant, can be measured by two independent methods: by studying the cosmic microwave background from the early universe, and by measuring distance indicators, Cepheid variable stars, Type ER supernovae in the local universe. The two measurements disagree. The early universe method, primarily from the Planck satellite, gives a Hubble constant of approximately 67.4 km per second per megaparsec. The local universe method gives approximately 73.2. The disagreement is 4 to 5 standard deviations, beyond the threshold that normally signals a real physical discrepancy rather than measurement error. Gravitational waves from binary mergers offer a third, completely independent method for measuring the Hubble constant. Because the intrinsic luminosity of a gravitational wave signal, the actual power emitted, can be calculated directly from the masses and orbital dynamics of the merging system. And because the observed amplitude of the signal decreases with distance, a single well-measured gravitational wave event can provide a direct measurement of its source's distance without any calibration steps. If the host galaxy of the merger can be identified and its recession velocity measured, the Hubble constant can be extracted. GW 17081, the neutron star merger detected in 2017, with an associated electromagnetic counterpart that allowed the host galaxy to be identified, produced a Hubble constant measurement of 70-8 plus 12 km per second per megaparsec, consistent with both camps but not precise enough to distinguish between them. With a larger catalogue of standard siren events, gravitational wave mergers with electromagnetic counterparts, the precision improves. The current LIGO catalogue is beginning to contribute statistically meaningful constraints, but the statistical uncertainty is still larger than the current disagreement. Resolving the Hubble tension with gravitational waves requires a larger catalogue of events with identified host galaxies, which requires either more electromagnetically bright events. Neutron star mergers produce light, black hole mergers generally do not, or statistical methods that work without individual host galaxy identification. Both approaches are being pursued. The tension remains, and if it is genuine, if the universe is expanding faster in the local region than early universe physics predicts, then something is wrong with either our standard cosmological model, our understanding of dark energy, or our measurement of one or both of the comparison datasets. Gravitational wave astronomy may be the instrument that eventually tells us which. The second pressing question is about the events we are not detecting. Every detection in the LIGO catalogue is an event that was loud enough, in the right frequency band, and of the right type to be found by current search algorithms. There is a population of events, possibly a large one, that is too quiet, too brief, too poorly modelled, or in too crowded a part of the data to be individually identified, and that is contributing to the background noise rather than the event catalogue. The development of better search algorithms, improved noise characterization, and more sophisticated matched filter templates is an active area of research that is making inroads into this invisible population. But for now, the catalogue is a bias sample. It is weighted toward the loudest, most symmetric, most theoretically expected events. The strangest events, the ones that don't match existing templates, are the ones most likely to slip past the current search methods. GW231123, with its anomalous ringdown, was only identified as a significant candidate event after significant dedicated analysis effort. How many similar events are hiding in the archive, waiting for improved analysis methods to reveal them? Nobody knows, but the answer to that question might contain some of the most important physics in the entire dataset. The fourth observing run of LIGO Virgo Cagra ended on November 18, 2025. The detectors are now in an upgrade phase, preparing for a fifth observing run with improved sensitivity. But the upgrade cycle of the current generation of instruments is approaching its practical limit. The LIGO facilities were designed with a specific length, 4 kilometers, and a specific optical configuration, and while incremental improvements continue to be made, the sensitivity cannot be improved by an order of magnitude within the existing infrastructure. To make the next leap, to push gravitational wave astronomy to the level where it can resolve the Hubble tension, study the ringdown of black holes with sufficient precision to test quantum gravity models, and detect every binary merger in the observable universe, requires new instruments of a fundamentally different scale. Two concepts are in advanced planning for the next generation of ground-based gravitational wave detectors, targeting operation in the 2030s. The first is Cosmic Explorer, a proposed American facility that would extend LIGO's basic architecture to an arm length of 40 kilometers, 10 times longer than the current LIGO arms. Because the sensitivity of a laser interferometer scales with arm length, a 40-kilometer instrument would be approximately 10 times more sensitive than advanced LIGO at the same optical power, with improvements in quantum noise squeezing extending this further. At Cosmic Explorer sensitivity, the detectable volume of space expands as the cube of the distance. A 10-fold increase in distance means a 1,000-fold increase in volume. The entire observable universe out to the epoch of reionization, when the first stars lit up roughly 600 million years after the Big Bang, would fall within the detection range for stellar mass binary black hole mergers. Cosmic Explorer would not merely expand the catalogue, it would allow gravitational wave astronomy to become a cosmological probe, studying the merger rate of black holes as a function of cosmic time and directly tracing the history of star formation and black hole growth from the cosmic dawn to the present. The second is the Einstein Telescope, a proposed European facility with a triangular geometry and arm lengths of 10 kilometers, designed to be built underground to reduce seismic noise and to operate at cryogenic temperatures to reduce thermal noise. The Einstein telescope's triangular geometry, 3 nested interferometers arranged in a triangle, allows it to measure all components of the gravitational wave polarization tensor simultaneously, giving it sensitivity to the shape and direction of the wave that a single L-shaped interferometer cannot achieve. This is not a minor technical advantage. Full polarization sensitivity opens qualitatively new observational possibilities, including the measurement of the gravitational wave polarization modes predicted by alternative theories of gravity. General relativity predicts exactly 2 polarization modes. Many alternative theories predict additional modes. Detecting or excluding these additional modes at cosmic explorer or Einstein telescope sensitivity would represent a definitive test of general relativity in a regime inaccessible to current instruments. Together, Cosmic Explorer and the Einstein telescope, operating as a global network alongside upgraded versions of LIGO and Virgo, would create a detection capability that is, in its potential scientific impact, roughly analogous to the transition from pre-Galilean naked-eye astronomy to the era of large ground-based optical telescopes. The number of detected events per year would increase from hundreds to tens of thousands. The precision of individual event parameter measurements would improve by factors of 10 to 100, making black hole spectroscopy tests of the no-hair theorem and quantum gravity constraints routine rather than exceptional. The standard siren measurements of the Hubble constant would reach the precision needed to resolve the current tension between the 2 existing measurement methods, and the detection of gravitational waves from core collapse supernovae, events that are in principle detectable by current LIGO but have not yet been seen because the last galactic supernova was in 1987 and the expected rate is only a few per century in our own galaxy, would open the door to gravitational wave observation of the processes that produce neutron stars and black holes in the moment of their creation. Beyond the ground-based next generation, LISA, the Laser Interferometer Space Antenna, is planned for launch in approximately 2035. LISA consists of 3 spacecraft separated by 2.5 million kilometers, connected by laser beams to form a triangular interferometer in space, orbiting the Sun in a configuration that trails Earth by about 20 degrees. The baseline of 5 million kilometers gives LISA sensitivity to gravitational waves at frequencies between 10⁻⁵ and 10⁻⁻⁴ Hz, far below the frequency band accessible to ground-based detectors, and precisely the range where supermassive black hole binaries, extreme mass ratio inspirals, and intermediate mass black hole mergers emit their gravitational waves. LISA will detect the mergers of supermassive black holes at the centers of galaxies as they merge, not as post hoc statistics, but as individual events, tracked over months or years as the black holes spiral together, with an expected signal-to-noise ratio in the millions for the nearest and most massive mergers. For the first time, we will be able to watch the merger of the monsters that govern galactic evolution as it happens, measure the parameters of the merger with extraordinary precision, and observe the electromagnetic counterparts, the jets, the accretion disk flares, the gamma-ray outbursts that accompany the gravitational wave signal. LISA will also detect the gravitational wave signals from tens of thousands of binary white dwarf systems in our own galaxy, objects so numerous that their signals will overlap into an unresolved galactic foreground that will itself carry information about the binary population of the Milky Way. The combination of ground-based next-generation detectors and LISA will create for the first time a gravitational wave observatory, covering the full frequency range from nanohertz to kilohertz, essentially the entire spectrum accessible from the size scales of stellar compact objects to the size scales of supermassive black holes. Multi-band gravitational wave astronomy. The joint analysis of signals seen by multiple generations of detectors at different frequencies will allow individual events to be tracked across years or decades, the in-spiral phase observed by LISA, years before the final merger enters the band of ground-based detectors. There is also a more speculative but genuinely exciting possibility: the detection of gravitational waves from the inflationary epoch itself. If the universe underwent a period of exponential expansion in its first 10-32 seconds, as the standard inflationary model predicts, then quantum fluctuations during that epoch would have generated a background of gravitational waves spanning all frequencies with an amplitude and spectrum that depends on the detailed mechanism of inflation. This primordial gravitational wave background has not been detected in the cosmic microwave background polarization, where it would manifest as a distinctive pattern of B-mode polarization, and its amplitude at LIGO frequencies is almost certainly too low for current instruments to see. But the next generation of ground-based detectors and LISA, with improved sensitivity over broader frequency ranges, will push into the parameter space where some inflationary models predict the signal should be detectable. If a primordial gravitational wave background is measured, it would be the most direct observational window ever opened on the physics of the universe's first moment. None of this is guaranteed. Science rarely delivers what it promises on schedule, and the history of gravitational wave astronomy is itself a story of timelines that stretched far beyond initial optimism. LIGO's construction took longer than planned. GW 150914 came earlier than expected. The event rates have been both higher and more diverse than the early estimates suggested. The next generation of instruments will reveal surprises that no current theoretical framework has anticipated. That is not a criticism of the science. It is the definition of what it means to open a new window on the universe. What I am confident about is this: the gravitational wave universe is not quiet. It was never quiet. For 4 billion years of Earth's history, the fabric of space-time surrounding our solar system has been rippling with signals from colliding black holes, merging neutron stars, exploding cores, and the slow spiraling together of objects so dense that space-time itself cannot hold its shape in their presence. We heard none of it. We had no ears to hear it. In September 2015, we grew the first pair of ears sensitive enough to register the sound. In January 2025, we heard one of the clearest notes yet struck in that cosmic symphony, and we have only begun to understand what the music is saying. There is a photograph I find myself returning to. It is not of a black hole, or a gravitational wave signal trace, or any of the instruments we have discussed. It is a photograph of Rainer Weiss in 2017, sitting in a chair at MIT, shortly after learning he had won the Nobel Prize. He does not look triumphant. He looks tired and satisfied and a little disbelieving, as though the thing he has spent his professional life building finally arrived. And the arrival turns out to feel not like a destination, but like a door that opens onto another corridor. That quality, that sense that every answer contains a question larger than itself, is, to my mind, the defining characteristic of physics at its best. GW 150914 confirmed that gravitational waves exist and that general relativity was correct about what two colliding black holes produce. GW 170817 confirmed that gravitational waves travel at the speed of light. GW 250114 confirmed the Kerr nature of rotating black holes and the Hawking area theorem. Each confirmation was profound. Each one also opened a new set of problems more intricate than the ones it closed. The pair instability mass gap is real, and it has been violated. How? The ringdown of GW 231123 does not sound quite like the Kerr prediction. Why? The Hubble tension persists. What resolves it? The information inside a black hole must be preserved by quantum mechanics, and quantum mechanics and general relativity are incompatible at the scales where both apply simultaneously. What theory contains them both? None of these questions have clean answers yet. Some may not have clean answers in our lifetimes, but the fact that we can now ask them empirically, not as thought experiments, not as theoretical speculations, but as questions with data attached, is the consequence of 50 years of work by thousands of people, many of whose names will never appear in a Nobel citation, building an instrument that most of the scientific establishment, once considered a monument to wishful thinking. Consider what the universe has revealed about itself in the 10 years since that first chirp was recorded in Louisiana and Washington. We have learned that stellar mass black holes are common, ubiquitous even, that they find each other across billions of years of cosmic time and merge in fractions of seconds, that the merger produces an object of extraordinary simplicity, described by two numbers exactly as Einstein's equations predicted, that those equations are robust, accurate, verified to extraordinary precision in the most extreme physical conditions we have yet been able to probe, and that the universe contains, in its most violent processes, violations of our most carefully constructed models, black holes in forbidden mass ranges, ring-down tones that don't quite fit, merger rates that strain our models of star formation and galaxy evolution. There is something genuinely poignant about the fact that Rainer Weiss died on August 25, 2025, just 16 days before the publication of the GW25011T paper, the analysis of the clearest gravitational wave signal his instrument ever recorded, confirming with a signal-to-noise ratio 10 times better than the first detection the theories of two of the other great physicists of his century, Hawking's area theorem and Kerr's rotating black hole solution. He almost certainly knew the preliminary results before he died. The analysis had been circulating within the collaboration for months. I find some comfort in that thought, that the man who spent his professional life listening for the universe to speak finally heard it speak more clearly than it ever had before, and heard it confirm the predictions of the colleagues he had spent decades in conversation with. Science is a collective act conducted across generations. The equations that LIGO confirmed were written by Einstein in 1915, derived by Kerr in 1963, developed by Hawking in 1971. The instrument that tested them was conceived by Weiss in 1972, funded over decades of skepticism, built by thousands of engineers and physicists, operated through 4 observing runs, and refined into the precise instrument that recorded a signal from a collision that happened 1 billion years before the first animal evolved on Earth. The lineage from Einstein's paper to GW25011Phi is a human chain stretching across 110 years, a single unbroken thread of curiosity and stubbornness and accumulated technical ingenuity. And it is not finished. The thread is still being pulled, LISA is being built, Cosmic Explorer is being designed. The 5th observing run of LIGO Virgo Cagra will begin, and the detections will resume, and somewhere in the data of the coming years there may be a signal that doesn't fit, a ring-down that no Kerr black hole should produce, a mass that no stellar evolution model can explain, a polarization mode that general relativity does not predict. That signal might not be found immediately. It might be hiding in data that is already sitting on LIGO's servers, waiting for an analysis method sophisticated enough to find it. It might arrive tomorrow, or it might arrive in a decade. The universe is not on a schedule that accommodates human impatience, but it is generous with its revelations in the end. It has been sending these signals for billions of years. Every collision of every black hole that has ever occurred in the observable universe has sent its ripples outward through space at the speed of light, in every direction, forever, a record of the violence that shaped the structure of the cosmos, encoded in the curvature of space itself, available to any civilization patient enough and technically capable enough to build the instruments to read it. We built the instruments, we started reading. We are, perhaps, 10 pages into a book of inconceivable length. The collisions will continue, the signals will arrive, the instruments will improve, and the question that lives at the centre of all of this, the question of whether the universe at its most extreme obeys the equations we have written for it, or whether it is stranger than our best minds have so far imagined, will continue to be asked by people who have not yet been born, using instruments that have not yet been designed, about events happening right now, 1 billion light years away, that will not arrive at Earth for 1,000 million years. That is the timescale this science operates on. That is the scale at which the universe invites our attention. And the honest answer to what we have found in all of these signals, in all of these confirmations, in all of these provocative anomalies, the honest answer to what two black holes colliding 14 billion years ago whispered to us through the curvature of space in January of 2025 is not an ending, it is a beginning that has been a long time arriving.